Hey everyone, and welcome back to the channel. Today we are diving deep into the exciting world of porphyry, copper and gold exploration. And I'm asking a crucial question. Are you missing these new signals? If you're a junior or senior geologist, an earth science student, or just a curious mind fascinated by how we find the hidden treasures of our planet, then buckle up. We're going to explore how our understanding of these massive mineral deposits has evolved and how cutting-edge techniques are helping us uncover them even in the most challenging locations. Finding giant copper and gold deposits is like being a detective on a planetary scale. These systems are the primary source of copper globally, supplying about 70% of the world's needs, and they often come with valuable byproducts like gold, molybdenum, and silver. They're massive low-grade systems, typically containing 0.3% to 2.0% copper. But here's the kicker, they're getting harder to find. Many of the easy-to-spot outcropping deposits have already been discovered, so now we're looking deeper, undercover, and in complex geological settings. It's like playing hide and seek with the Earth, but the Earth is a very good hider. The Porphyry Playbook, a model that keeps evolving. Our understanding of porphyry deposits isn't static, it's a constantly evolving playbook. The core model dates back to the 1960s, but it's been refined to account for different intrusion chemistries, varying wall rock controls, and the effects of weathering and erosion. Recent advancements highlight several key areas. First, we're better understanding tectonic controls. Porphyries love subduction zones, those geological collision sites where one plate dives beneath another. But it's not just any subduction. Specific perturbations like small collisions or oceanic plateaus interacting with subduction zones can create the ideal conditions for these giant deposits. These events promote magma fractionation and the generation of those precious magmatic hydrothermal fluids at shallow crustal levels, often bringing the deposits closer to the surface due to uplift. The challenge, of course, is applying this knowledge to ancient environments where the evidence might be a bit dusty. Second, we've gained better knowledge of different porphyry subtypes like the alkalic porphyries. These behave a bit differently than their calca-alkalic cousins, with more complex alteration patterns and calcium-bearing minerals in their cores. And third, thanks to detailed studies of fluid and melt inclusions and advanced geochronology, we have a clearer picture of the fluid compositions and the history of magmatic hydrothermal activity that creates these deposits. We're essentially peeking into the past to see how these massive ore bodies formed, which is pretty cool, if you ask me. Old dogs, new tricks, evolution in exploration techniques. For years, traditional field geology and geochemistry were the superstars of exploration, and they're still incredibly important. But their roles are evolving. Surface sampling is still useful, but increasingly the real insights come from drill hole samples. This is where we get up close and personal with the rocks, gathering detailed geological, geochemical, and geophysical information that helps us vector toward discoveries. Think of it like this. Instead of just looking at the topsoil, we're now digging down and sending in a microscopic forensics team. This shift has led to higher discovery rates in covered settings and at greater depths. Let's break down some of these crucial new signals and techniques. Geochemistry, the invisible trail of riches. Geochemistry, the study of the chemical composition of Earth materials, is revealing subtle clues. Sulfur Isotopic Zonation, this is a fantastic new vectoring tool. By analyzing the sulfur isotopic compositions of sulfide minerals like boronite, chalcopyrite, and pyrite, geologists can map systematic zoning patterns around the high-grade core of a deposit. Many porphyries show strongly negative sulfur isotopic compositions in their cores, transitioning to near zero values on their peripheries. It's like following a breadcrumb trail of sulfur straight to the metallic jackpot. Indicator minerals. These are like geological bloodhounds. Analyzing specific minerals from drill cores or even surface sediments can tell us a lot about the fertility of the magma and the physicochemical conditions during ore formation. Imagine finding a tiny mineral crystal that whispers, "Copper here." Pretty powerful stuff. Geochemical halos and erosion levels. We can also use geochemical halos in soil samples to figure out if a deposit is above or below the current erosion surface. For example, at the North ROK Porphyry deposit in British Columbia, scientists used elements like copper, molybdenum, lead, and zinc in soil samples, along with 3D modeling to determine if the deposit was a supra-ore body. This kind of insight can significantly reduce the risk and cost of exploration drilling, because who wants to drill where the good stuff used to be, right? Geophysics, seeing through rocks. Geophysical methods allow us to see what's hidden beneath the surface. Magnetic exploration, this is a big one. Porphyry systems often contain varying amounts of magnetic minerals like magnetite, which can be present in the mineralization, alteration, or host rocks. Detailed magnetic data, whether from airborne or downhole surveys, has been instrumental in recent discoveries. For example, gold-rich porphyry copper deposits often have abundant magnetite in their potassic alteration zones, creating a distinct magnetic high. Conversely, some high-sulfur systems have extensive magnetite destructive alteration, which can produce a magnetic low, often surrounded by magnetic highs in less altered rocks. It's all about understanding these magnetic fingerprints to interpret the hidden geology. Induced polarization, IP. IP surveys help us map the distribution of sulfide minerals, which are often associated with ore bodies. Advances in computer technology have drastically improved the acquisition and interpretation of IP data, making it a critical, albeit indirect, tool for pinpointing deposits. Gravity surveys. While less commonly used than magnetics due to cost and modeling complexities, gravity surveys are gaining traction as airborne costs decrease and we explore more covered terrains. They can help detect density contrasts associated with alteration or mineralization. Remote sensing, eyes in the sky. Why get muddy when satellites can do the initial legwork? Multispectral data, ASTER and WorldView-3. Satellites like ASTER and WorldView-3 are revolutionizing how we map hydrothermal alteration zones. ASTER, with its medium resolution, is great for regional mapping, while WorldView-3 offers very high-resolution data, allowing for incredibly detailed analysis at a local scale. These sensors measure spectral reflectance in different wavelengths, which helps us identify characteristic alteration minerals like kaolinite, elite, montmorillonite, indicating argillic alteration, chlorite, epidote, calcite, propylitic alteration, and cerisite, quartz, and muscovite, Phyllic alteration. Case in point, Aidarly Deposit, Kazakhstan. In a recent study, researchers used ASTER and WorldView-3 data to delineate hydrothermal alteration zones near the Aidarly Deposit. They didn't just confirm known mineralization, they actually identified a previously undocumented hydrothermal zone exhibiting concentric phyllic and argillic alterations, potentially an extension of the mineralized system. That's like finding a secret room in a house you thought you knew inside out. This demonstrates a reproducible and scalable workflow for early-stage exploration, especially where field access is limited. The AI revolution, deep learning and unsupervised machine learning. This is where things get really futuristic, but it's happening now. Mineral prospectivity mapping, MPM. Traditionally, MPM often relied on expert judgment, which is great until deposits are hidden under thick cover, making it tough for even the wisest geologists. Enter data-driven methods, especially those powered by machine learning and deep learning. Unsupervised deep learning, GeoVT. Imagine an AI that can learn from vast amounts of geological, geophysical, and geochemical data without needing to be told what's what. That's what unsupervised deep learning methods like GeoVT, a vision transformer-based model, are doing. They fuse multi-source geoscience data, identify complex mineralization-related spatial anomalies, and distinguish prospective areas from background noise. Because mineralization is a rare event, geologically speaking, finding a deposit is like finding a needle in a haystack, or rather, a shiny gold nugget in a mountain of dirt. These models can spot subtle patterns that humans might miss, especially in concealed systems like certain IOCG deposits where traditional methods struggle. It's like having a super smart digital assistant doing all the grunt work of pattern recognition, leaving geologists free to interpret and make the big decisions. Tourmaline, more than just a pretty stone, even individual minerals are giving us new signals. Tourmaline breccia pipes. These distinctive deposits can host significant metal concentrations, and they often form in the shallow regions of porphyry copper deposits, transitioning into deeper mineralized intrusive suites. Studying their characteristics, formation, and variations helps us link them to potential porphyry systems at depth, essentially using them as natural drill holes that sample deeper geology. Boron isotopes in tourmaline. Tourmaline's chemistry, particularly its boron isotopic composition, acts as a mineralogical recorder of ore-forming processes. It can help reconstruct the thermal evolution of hydrothermal systems and serves as an effective vectoring tool in metallic ore systems. The composition of tourmaline can even indicate the redox state of associated intrusions, which is crucial for understanding whether a magma was fertile for ore formation. Putting it all together, the integrated approach. No single technique is a magic bullet. The most successful exploration efforts combine a broad range of these methods. Imagine a symphony where each instrument plays its part, creating a harmonious picture of the subsurface. Regional geophysics like airborne magnetics and radiometrics can provide a first-order filter to identify promising areas, even in less explored or covered provinces. Then, more detailed surveys, remote sensing, and geochemical analyses are layered on top, followed by targeted drilling and drill core analysis. This integrated approach helps us understand complex geological models, which are far from simplistic. Porphyry systems can be tilted, disrupted, or have asymmetric alteration zoning due to their interaction with different country rocks. Rapid uplift, for example, can lead to the telescoping of mineralization where porphyry and epithermal deposits form in close vertical proximity, or even enhance the copper grade of a deposit. Recognizing these geological nuances is key to interpreting the signals correctly. The missing porphyries, a lesson from Japan. It's fascinating to note that despite Japan's tectonic setting being ideal for porphyry deposits, none have been definitively found there yet. This paradox highlights a crucial point. Exploration often stops too early, especially before benefiting from significant metallogenic and technological breakthroughs. Japanese geologists focused on other deposit types for decades, but new insights suggest that porphyries likely exist deeper beneath known epithermal and VMS volcanogenic massive sulfide systems. This reminds us that sometimes the missing signals are just waiting for us to use the right tools and keep looking. The future is now. We are truly in an exciting era for mineral exploration. The integration of advanced technologies like high-resolution remote sensing, sophisticated geophysical modeling, cutting-edge geochemistry, and artificial intelligence is not just a trend. It's becoming the standard. These new signals are empowering geologists to look beyond the obvious, to peer deeper beneath the cover, and to identify the subtle clues that point to the next generation of giant porphyry, copper, and gold deposits. So, are you missing these new signals? The answer, I hope, is a resounding not anymore. Keep learning, keep exploring, and keep pushing the boundaries of what's possible in Earth science. The next big discovery might just be a few clicks or a few drill meters away. Thanks for watching, and I'll see you in the next video.